Hello, my name is Jeff Passmore. I work for JDSU's sales support organization, and I'll be your host today for today's session discussing the resistance measurement on the HST3000. In our last session, we left off on DC current, and following along with the theme of using the down arrow under DBOM, if we press down arrow from current, we will go to a resistance measurement. However, it's resistance snapshot. So we discussed early on we're not crazy about snapshot. So if we hit down arrow again, we'll go to resistance continuous. Now, I don't want to appear as though I'm down on our snapshot measurement. The main reason for showing you what I just displayed was you did not have to wait for that resistance snapshot to finish, right? If you knew you wanted to go to the continuous, you just hit your down arrow button a second time and you would go there. So keep that in mind. You're running the tester. Don't let the tester run you. So we're at the second of the three core measurements that we said we almost always make, right? Cross battery and now shorts and grounds. I have a good time discussing resistance measurements with training classes because quite often I'll pose the question of what the particular group of technicians use as a pass-fail parameter for resistance. In other words, what does that number have to be? Uh, Quite often I am met with just a dead silence. Well, it's generally accepted across North America if the number is greater than 3.5 million ohms, the circuit is good enough for pot service. So that's greater than 3.5 M. Well, how high do you read, Jeff? Well, greater than 999 million ohms, almost a gigaohm. Orders of magnitude higher than what most phone companies use as a pass-fail parameter. Logical question might be, well, why do you measure so high? Well, personally, I think there's a bit of marketing involved. I can remember when test sets read greater than 10 meg, someone moved it up to greater than 100. One of the prominent manufacturers were the first to go to greater than 999. Well, from our side of the business, not that you folks care at all, you can't afford to have the box with the lowest number. So we're all sitting at greater than 999. Crazy high in my opinion. As a cable maintenance person, I never took 20 mega ohm of trouble off of anything and had it make a difference, right? It's just too high of resistance. Now, in our later follow-ups sessions, when we start discussing wideband, I'll revisit this resistance measurement and give you a practical example of why this much resistance range is useful, especially for IPTV. But it doesn't fit into our conversation right now. For all practical purposes, greater than 999 is crazy high. Notice that the screen looks the same, operates the same as the previous, right? Left and right changes the lead combination. I got my lowest and highest down there, so if, for example, I thought I had a bad aerial drop, say, going through the trees, I could put my HST on continuous tip and ring resistance, go get my layup sticks, wiggle the drop around, come back and see if it did anything. Yeah, you could. I mean, again, a simple example, but a practical one because any change would be captured down here, right? How does an ohm meter work? Well, that sounds kind of goofy, doesn't it? I mean, I knew how to run one the first week I was there. I darn sure didn't know how they work. I'm going to switch over to my whiteboard. When you hook an ohm meter up to a line, you're essentially hooking up a DC battery. Now, my engineer kind of doesn't like me using that definition primarily because there's a whole bunch of magic that goes on inside the HST's ohm meter. But for the most part, you and I don't care about that. We just care about results. So if I hook up a cross tip and ring, I'm essentially just putting a DC battery on the line. Well, you and I are going to build a case of trouble. I am going to say that on this particular cable pair, I have put a Scotch lock across the end of it. So I have dead shorted this pair. Well, as we said when we discussed the current, when you short a battery, current starts to flow. So when I lay my ohm meter across the cable pair that's shorted, current flies out of one of those leads, right? Because it senses a continuity path or a place to get to the other side of the battery because that's all it wants to do. So current will fly down one lead, find the continuity point, short, and all it wants to do is get back to the other side of the battery. Well, when current flows in an analog meter, it moves the needle. So that's essentially what's going on. Now, I'm sure most of you are experienced enough to know that if you have a dead shorted cable pair and you know the gauge of the cable, you can convert that ohm reading into distance, right? That's called ohms to feet. Well, I'm going to give you that part. I'm going to say it's 24 gauge cable. I'm going to say your ohm meter reads 51 ohms, and that equates to 1,000 feet of loop resistance. Now that ohms to distance equation is found in the HST under the F1 display key. So this is what it would equate to. 24 gauge 51 ohms means the short is 1,000 feet away. Now, an important note on our ohms to distance calculation, a lot of manufacturers, when you are looking at a short, will give you a distance back that you have to cut in half again to get to the location of the short, because the distance they'll provide you back is the overall loop length, right, out and back. Well, that never made sense to us. I mean, we always thought, well, heck, you're looking at a short, you're interested in where the short is, right? So we cut it in half for you. So any distance you receive will be a distance to the short. The other thing I'm going to tell you about this case of trouble that you normally wouldn't know when you were out there, but all I want you to do is clear your mind and listen, is between you and the short, there's a great big fat bridge tap. Now there is no fault on the tap. It is clean as a whistle, but by golly, it's right between you and the short. Knowing what you know about this case of trouble, I'm going to ask you a yes or no question. When you think about it, you got a 50% chance of being right before you even know what the question is. Knowing what you know here, could I, yes, still trust my distance to short, or no, I could not trust it because the bridge tap would screw me up? Well, again, we're doing a recorded session. I'm not expecting any answer, but unfortunately, I have to report that more than half the technicians get this wrong, this question wrong. Yes, you could still trust the distance to short. All right. When the DC current flies out of one side of that meter, it sees the bridge leg, all right, but it instantly sees there's no continuity path. There's no place for it to go. So it ignores it entirely. It finds the continuity path, and the same thing on the way back. It sees the other side of the bridge tap, but it instantly senses there's no place for it to go. So it ignores it entirely and just goes right back to the meter. So in theory, heck, I could put 50 bridge taps on there as long as they were not faulted. They would have no impact on my DC current measurement used for my ohms meter. Well, here's part number 2. Instead of a short, we have an open. And between us and the open is that same unfaulted bridge tap. Okay? Well, if it's an open, we don't care about gauge and ohm values anymore. All right. So here's my open. Between me and my open, I've got that same bridge tab. Same question. Knowing what I know about this case of trouble, could I trust the kick on my analog meter, or could I trust my open meter to give me the right location? Well, I'm happy to report that everyone always gets this one right. The answer is no. The bridge tap would mess you up, right? Probably because everybody's been burnt by that one time or another, right? I know I certainly was. Now, when I refer to kick on an analog meter, for those of you that still have an analog meter, there's a bunch of them out in the field. There's usually a switch associated with the meter. There was on mine anyhow. And that switch was labeled REV. Now, I didn't know what that meant. All I knew is that that is the switch that I would toggle back and forth to get the needle to deflect or move, right? And based on its deflection, I could calculate in my head about how far that was distance-wise. Well, what that REV switch did actually to the meter was reverse the polarity of the battery. I tell telephone people that I train we only have two types of battery to deal with. One is DC. It's got a constant polarity. It flows current in one direction. The other one's a little bit unpredictable. First he has one polarity, then he has another. We call him AC. So when I'm kicking with that reversing switch, believe it or not, I'm putting a real crude AC signal on the line. Now, what's your point, Jeff? My point is, any AC signal will go any place there's cable for it to go, right? So it goes down this way. It most certainly also goes down this way, right? Because that's why we knew our measurement would be inaccurate with the bridge tap in front of our open. Well, I'm going to ask you a silly sounding question. Believe me, there's no tricks, especially on a recorded version. It's going to sound silly, I promise you. If we weren't going to have customers that paid us for the ability to talk on telephone lines, or paid us for the ability to surf the internet, or paid us for the ability to watch TV, do you think we'd have very many customers? I told you it was going to sound silly. Of course not. If we weren't going to talk, surf, or watch TV, what the heck would we be doing? What would we be selling them, right? Well, all of that stuff, my voice, surfing, and IPTV, all consist of AC energy. My voice is AC, your voice is AC every time you speak into a telephone, right? It's converted to an AC signal. DSL is nothing more than a series of high-frequency AC, but AC nonetheless, right? So when you think about it, we're actually in the AC transport business. If we were not going to transport these signals, heck, we wouldn't even be here. Well, that's pretty important. It's pretty important. If this is the only reason we're here, it's vitally important that we understand how these signals act on a cable pair. Well, heck, you already knew, right? AC goes any place there's cable for it to go. So it's going to go this way, it's going to go this way. If I put another bridge tap on it, won't it also go down this leg as well? Bigger kick yet, right? Well, as directly opposed to DC, which needed continuity for it to travel, right? I needed continuity. All right, let's go back to the HST. Very important to understand, I believe, primarily because when I worked outside, I for a long time thought if the cable pair wasn't crossed, if it wasn't shorted or grounded, and if it wasn't open, I had a good cable pair. Well, nothing could be further from the truth. All you had was continuity between point A and point B. You hadn't done anything to check the quality of the pair's ability to transport AC signals. So back to our innocent old ohmmeter. If it's nothing more than a battery, how much battery does your ohmmeter put out, Jeff? Well, in this mode right here, I put out 30 volts DC. Right. If you look under F4, it lines up with the word that says leakage. If you press F4, the lightning bolt appears on the screen. That's an indication that the 30 volts has gone to 120 volts. Now, the 120 volts is a current limited supply. All that means is it cannot hurt you. It'll tickle you well. If you're grounded good, you'll certainly know it's there, but it's not going to hurt you or harm you. The thought being the 120 will look harder for a shorter ground than the 30. Well, I don't really know if that's true or not, but I do know when I'm riding with you folks measuring cable pairs, more often than not, I will pop it with the leak button just to see what happens. A note on this 120 volts, it is a super high impedance supply. What I mean by that is if you wanted to pick up an ordinary meter and just measure for that voltage coming out of the ohm meter on the HST, you would not see anything near 120. You would have to have a real high impedance lab type meter to see the actual voltage come out. Alrighty, what else on the ohm meter? For those of you that have used an analog meter, have you ever run across a case of trouble where the line would show grounded, but the minute you hit the reversing switch, the ground would disappear? Well, I'm grounded, but I hit my REV switch, boom, the ground's gone. That happened to me a few times outside. It was a case of a mysterious ground. I didn't know what the heck was going on. Well, really, what you're seeing in that situation is the effect of a polarity-sensitive fault or a diode fault. Now, there are tons of things in the DSLAM and in the customer's equipment with diodes in them. You know, diodes block the flow of DC current in one polarity, but if you reverse the polarity, it allows the current to go right through it. All right? It's an electronic component. The thing that acts or mimics a diode in the field from fault standpoint is the green corrosion we quite often find on connectors or crossbox terminals. That green substance is actually the substance they made the first diodes out of, so they're sort of naturally occurring diodes. You know, the reason I'm giving you this semi-history lesson is unbeknownst to you, in the background, the HST is constantly hitting its reversing switch over and over and over again, just like you do or did with your analog meter, all in an attempt to make sure you don't miss a diode fault. One word about the number. Making a transition from a needle to a number was one of the most difficult things I had to do as a telephone technician. I knew I was measuring resistance. I didn't pay any attention to that. I paid attention to how far the needle moved. Right? Making the transition from the needle to the number was hard. The way I did it is I remembered the 3.5 M. Right? If any number came back with the letter K next to it, it was in trouble. And if any number came back with no letter next to it, it was really in trouble. Now that sounds a little patronizing. Remember, I'm not talking about you. I'm talking about the way I remembered it. One interesting thing I did find out, though, is once I got my head around the first set of numbers, the second set of numbers were that much easier to grasp. So I don't know if you will make the transition from the needle to the number. I do bet, however, that you won't disagree with me when I say that your phone company is throwing more and more numbers at you all the time, right? I just found that once I understood the first set, the next set was that much easier. And finally, to wrap up the ohm meter, on our analog meters, every so often we would have to zero them out or calibrate them. Well, you can do that same function on the HST. You would find the button labeled Configure right underneath Cancel. When you press Configure, it takes you to the Ohms Compensate screen. Here, you just follow the directions, short all three leads, right? Clip them all three together, and press F4 to compensate. This gets rid of any resistance in the test leads themselves, right? Zeroing the meter out, we used to call it. Once it's complete, it will come back and tell you it's complete and stamp the date and time that it did it, just for your reference. Now, when you hit cancel to go back to the ohm screen, you should see 0 ohms if your leads are shorted together in all 3 spots, right? So 0 tip to ring, 0 ring to ground, and 0 tip to ground. All right, that concludes our discussion on the resistance meter. We thank you for attending, and I certainly hope it was worth your while. And our next session will cover the opens test. So thank you again.